Greetings, students. Today we are going to finish our discussion of confidence intervals, and we're going to finish it with creating confidence intervals for population mean. In the past, we created the confidence intervals for population proportions. First, let's remember what the confidence interval is and why we need them. We're not going to write anything there. We're just going to verbally remember that the confidence interval creates the interval in which your true value of the population is supposed to lie. So um, now we cannot ever be 100% certain that the true value actually lies in that interval, but we have something called the confidence. We can create a 95% confidence interval, 99% confidence interval, and so on. And please remember that the more confident we are, the bigger the interval is. So we paying for the accuracy of our true value with our confidence and other way around. Why do we need them? Well, that is one of the ways that allows us to predict what the true population value is. So we can never truly find the actual population value, but we at least can see the interval in which that value lies. So today we're discussing the confidence interval for means, and we are going to talk about a new distribution called the T distribution, and we'll discuss why we need to talk about this new distribution. So first of all, let's remember how do we find a confidence interval. So there is a general formula for the confidence interval that is the following. You take the statistic, and remember, statistic is the value that you find from the sample, plus or minus critical value, and you multiply that critical value by the standard deviation of the statistic. So we learned how to find the confidence interval for proportions in the previous lesson, and it looked like the following. So in this case, the statistic was p hat, which is a sample proportion, plus or minus critical value, which was our z-score, times the standard deviation of the statistic, which was given by the following formula. However, we also discussed how our p is the true population proportion, but we can never truly know what the true population proportion is, because if we do know it, we don't really need the confidence interval anymore. So therefore, we replaced the standard deviation of the statistic with standard error. And by standard error, I mean is that we replaced our population proportion with the sample proportion. So the true formula that we actually ended up using was the following, where our p were replaced with p hat, meaning that we used the proportion from the sample. So this was our formula for creating the confidence interval for proportions. Well, when we talk about the means, it's going to be similar setup, except our statistic for the means is not p hat anymore, but it's going to be x bar. Since we're talking about means, the statistic is the sample mean, which is x bar, plus or minus. And now we, and then plus or minus z times standard deviation divided by square root of n. So this is what it's supposed to be. However, there's another problem, similar to what we have with the proportions. We are talking about the standard deviation of the population. The problem is we don't generally know the standard deviation of a population, because if we know how to find the standard deviation of the population, then we know how to find the mean, and then we don't need the confidence interval. Therefore, we are going to replace this standard deviation with standard error. With standard error, which means that we are going to replace our standard deviation of population with the standard deviation of the statistic. However, by doing so, we also going to change our distribution. And therefore, our distribution will stop being the z distribution and will start being called something called t distribution. So let's talk about the t distribution, and then eventually we'll derive the actual formula for finding the confidence interval of for the means. So the formula that we're looking right now, that is the ideal situation that generally will not happen, because once again, we do not know the standard deviation of the population, uh, and the fact that we are changing our standard deviation of the population with the standard deviation of the statistic will also change this z. So this will be replaced. So we will discuss this right now. So as the note at the bottom says, we don't know the standard deviation of the population, so we have to use the sample standard deviation. And if we standardize based on the sample standard deviation, we get a different distribution, as already mentioned, and that's called a t distribution. So we're not going to get in too many details about the how it's all done, but here we have the examples. So this is our t distribution, and this is our normal distribution, or we can call it z distribution. So once again, if we're using a sample standard deviation, our distribution is no longer a z distribution, now it is a t distribution. So what is the difference between the two? Well, the major difference, we can see it from the picture, is that, well, first of all, there's similarities. They're both symmetric distributions. They're both roughly symmetric, or symmetric, but this is our t and this is our z, and we can clearly see that our t distribution is more spread out, which means that it has much more area at the ends or at the tails. So we see that the t distribution is a little bit different from the normal curve. It is symmetric and has a peak at 0, just like a normal curve, but it has much more area at the tails, which in other words means that it has larger intervals. Okay. Now, let's talk about the t distribution in a little bit more details, because the t distribution is what we will have to use in order to find our confidence intervals. So t distribution still tells us how far our sample mean is from the true population mean in standard deviation units. However, there is a different t distribution for each sample size. So once again, remember that we're using the t distribution because we are using a sample standard deviation. And if we remember the formula for finding the standard deviation depends on the sample size. Therefore, with every different sample size, we get a different t distribution. And we can see that in the formula here in a minute. So therefore, we have to specify a particular t distribution by giving what's called the degrees of freedom. And degrees of freedom we abbreviate as df, and it is equal to the sample size minus 1. So in other words, if we pick a simple random sample of size n from a large population that has a normal distribution with the mean mu and the standard deviation sigma, the statistic which will be our t, is equal x bar minus mu divided by the standard error, which is given by standard deviation of the sample over square root of n. So once again, notice that the standard deviation by which we divide depends on the sample size n, and because it depends on the sample size n, we have a different distribution for every different statistic. Therefore, that's why we have to use this degrees of freedom. And we can see that the t-distribution has the degrees of freedom n minus 1. Now, if the population distribution isn't normal, this statistic will have approximately t sub n minus 1 distribution if the sample size is large enough, and we will discuss what it means to be large enough. Okay, so right now this happens if the distribution is normal, if the population is normal. If population is not normal, we will discuss what needs to be done in that case here in a little bit. So if we look at this graph, so here we are comparing of what's happening with our distribution based on the degrees of freedom, or in other words, the sample size. So we can see that the dotted line, this dotted line that I'm highlighting right now, that is the distribution if our degrees of freedom is 2. So it basically means that our sample size is very small. Degrees of freedom of 2 means our sample is only 3 subjects. That's very small. Then if we get the degrees of freedom 9, so that's the situation. I'm going to highlight this with blue. And we can see that it gets a little bit higher and less spread. And then we can have a normal curve, and that's, I'm going to highlight it in yellow. So this is the normal curve. So what is happening is that as our degrees of freedom increase, so the bigger the sample size, then the t-distribution approaches the standard normal curve. So the t-distribution is never truly a normal distribution, but as our sample size increases, the distribution becomes more and more normal. So eventually we can basically say, hey, this is approximately normal. So in other words, we can see that the shapes are very similar to the normal curve. We can see that the spread of the t-distribution is a little bit greater than the normal distribution. Therefore, the t-distributions have more probability in the tails and less in the center than does the normal curve. And as we already discussed, as the degrees of freedom increase, the t density curve or the t-distribution approaches the normal distribution. So for t-distributions, we will be using also a table, just like we've done for z-scores and normal distribution. There is a particular table that will allow us to find certain probabilities. And that table is in your textbook. It's called Table B, and it's on page T3. I also have an uploaded PDF version of the table in the lesson, so you can download it and save it somewhere where you can easily find it. Now, the table is limited because it cannot account for every possible number of sample number. So sometimes the sample that you have, the degrees of freedom that goes with that sample is not portrayed in the table. So if that happens, then you should use the greatest degrees of freedom available, that is less than the desired degrees of freedom. So in other words, you will always round down. So less than, always round down. You also could use your calculator, and there's a function called inv_t. So if you want to use your calculator, that is perfectly fine. However, I generally don't show how to use this calculator function because I like you guys to be familiar with the table, and it will give you a little bit more practice using the table. So right now we are going to do a quick example where we'll discuss what is based on the sample size, what is going to be the degrees of freedom, and what is going to be the t-value that will be our critical value. So let's say we want to create a 90% confidence interval based on a simple random sample of size 10. So if our sample size is 10, then the degrees of freedom is very easy to find. It is just n minus 1. Therefore, it is going to be 10 minus 1, which is equal to 9. So that's the degrees of freedom. Now, what is going to be the t-value that goes with it? Well, for that, let's look at the t-table and learn how to read that, because it's actually a little bit different from the z-table. So I have a t-table right here. So in this t-table, it gives us the probability p that is to the right. So it gives us this probability right here, just one tail. So unlike the z-table, there are no two sides to it. We're just using one table, one side. Now notice that the probabilities are not written on the inside of this table. The probabilities are actually these top numbers right here. These are the top numbers. And also notice, it will be helpful in the future, that at the bottom of the table, we have this percent. These are the confidence intervals that go along with those probabilities. So we'll learn to find the confidence intervals in a slightly easier way. So in our case, and then on the left side, on the side of the table, we have the degrees of freedom. So all of the numbers right here, all of these numbers are the degrees of freedom. So in our case, we have 9 degrees of freedom. We have 9 degrees of freedom, and our confidence interval is 90%. So we can, for the ease of it, we can just find 90% confidence interval at the bottom of the table, and then go all the way up and match those up. And it looks like we are going to get 1.833, which also means that the tail has the probability of 0.05, which is 5%, which makes sense if we have a 90% confidence interval. So if we have a 90% confidence interval, this is our interval. That means that this area right here should be 5%, and then this area should be 5%. So it's broken up into those. So, but the probability P, we will actually be using that a little bit more in the future, but not yet. So in other words, we know the t value, which is 1.833. So therefore, we can write down that t is equal to 1.833. So that's how you generally use the t-table. Now let's look at example B. So we have a 99% confidence interval based on a random sample of 95 observations. So that means that the degrees of freedom is, of course, 95 minus 1, which is 94. And now based on this degrees of freedom, we need to find our value t. Well, here we run into a problem. So because if we look at our degrees of freedom, we don't get 94 degrees of freedom. So remember that our degrees of freedom is 94. We clearly don't see 94 in this table. And then remember that you always will round down. So even though some of you might want to use 100 degrees of freedom, we are not going to use that. We always round down. So the degrees of freedom that we have to use is much more conservative, and it has to be 80 because it's the closest available number, less than the degrees of freedom that we have, that we actually desire. So we're going to use 80 degrees of freedom, and then we find a confidence interval of 99, and therefore we end up with t equals 2.639. So once again, please remember that if your degrees of freedom are not shown in the table, you use you always round down and you use the lowest degrees of freedom available compared to what your desired degrees of freedom are. Okay, so that's what the T distribution is. In the next part, we're going to discuss the conditions for estimating the population mean, and then we eventually will actually learn how to find the actual confidence interval using the t-table, and how to find the confidence interval for the population mean.